Hello everybody, my name is Nomar Santiago and I am studying mechanical engineering here at the university. I'm at my 4th year and I am in the mechanical division design aspect of our group.
I'm Rico. I'm currently a third-year mechanical engineering undergraduate, working as a researcher under the mechanical division of the RoboBoat team.
And my name is Mayaguez. I am currently the mechanical division leader here at UPRM's very own RoboBoat team. I am currently in my 3rd year of mechanical engineering, and today we're going to be talking a little bit about our hull design.
Given our current situation regarding code regulations and our preferred safety measures, our workshop time has been drastically reduced. For this reason, we've decided that our original autonomous surface vehicle, called Rumba, would be returning to this year's competition. As stated by the Domination Challenge, our boat must meet certain criteria. The main criteria we want to emphasize is on the size and weight. The rules state that the boat will fit on a rectangular box of 6 feet of length with 3 feet of both height and width. Our boat must also weigh less than 100 pounds, keeping in mind that the more the boat weighs, the less points will be given to the team. The boat must also be positively buoyant, which means that it must float on its own. To satisfy these conditions, a combination of lightweight materials with a large hull giving us a bigger surface area was decided as the optimal design. Rigid PVC was chosen for its low density, cost, and high corrosion resistance in order to provide the desired buoyancy with minimal manufacturing needed. The walls were made with an angles greater than 90 degrees to achieve an accessible interior through the top, connecting the hull and the top sides of the boat with a latched entrance would provide for quick access to the interior, thus creating a rectangular boat with a converging front edge of the final product called Rumba.
As for competition strategy, given that our original hull design has performed well on previous competitions, this year we aim to fix the areas of the boat which were somewhat lacking in order to achieve an even better performance this year. The aspects of the boat that were modified include thruster mounts, full front hull geometry, boat lid, and a new cooling system design. Since our strong suits in terms of design have always focused on our manufacturability and low weight, it can be perceived that by the changes we apply to the thruster mounts and the front of the hull, we can also aim to reduce drag so that Rumba can also aspire for greater speed and also maneuverability. We started redesigning our thruster mounts. Originally, they were geometrically square wooden mounts that experienced significant drag when submerged. To fix this, we implemented C-shaped mounts that would reduce drag on the thrusters by reducing its surface area without actually having to compromise the stability of the mount. Next, Rumba originally had a flat front hull. After observing fluid dynamic simulations, we were able to see how the flat surface gave the boat such a large amount of resistance due to it being at such a steep angle in reference to the water. This problem was then solved by adding a small curvature to the boat front, which would part the water more efficiently and reduce water impact. Our final improvement was a complete redesign of the boat's lid. In 2019's competition, we encountered problems concerning water leakage into the boat's electrical components. As a response, we designed a locking mechanism, which would be lined with a sealing foam material and operated with a pressurized lock. Along with these improvements, we also reduced the lid size to provide a 1.5-inch clearance on all sides, which would not only make space for sensors, it would also allow for a shorter cable distribution. With these changes, we can nullify the chances of system failure by water leakage in our boat. But also, with all of the significant drag reductions we achieved, we can also expect to perform better at the Speedgate Challenge, for example. We are confident that all of these year's modifications will at least bring us a step closer to victory and set the path for future advancements in our team's hull design.
As for the simulations, the team used the Unity real-time development platform to simulate the tasks to scale as specified by the latest competition rules. This is done with the purpose of creating a user interface where the team can monitor the boat's interaction with the objects in the environment. that is, buoys of different models, shapes, and sizes, as well as observe its telemetry data. Furthermore, the simulation generates the objects detected in the boat's path, as well as a boat model to convey an atmosphere as similar to the one surrounding the real boat as possible. This way, we were able to theoretically test how well our boat should perform under the varying conditions presented during the race, as well as unprecedented environmental changes, allowing us to monitor its trajectory for the entire race and allow it to autonomously make changes based on said changes. This is possible through the use of cameras with vision detection algorithms and ultrasonic sensors on its sides to detect incoming objects and provide all the data required to analyze the boat's telemetry. The mounting for these devices are as follows. The camera is placed on top of the front part of the boat's hull, and a total of 5 ultrasonic sensors, 2 in the front edges next to the camera, 2 on the sides, and 1 on the back end.